Hello and welcome back. In the first video on Newton's laws, I mentioned that whenever an object is in contact with a hard surface, there are two types of forces that arise. There's the normal force, which we already talked about, and this is always perpendicular to the surface. In addition, there's also the frictional force, which I'm going to talk about in this video. This one is always parallel to the surface. Now it turns out that there are actually two types of frictional forces that we're going to talk about in this class anyways. And these are the static frictional force and the kinetic frictional force. The static frictional force is the frictional force that is exerted on an object that is at rest. Okay? So the static frictional force essentially acts like a normal force. So the static frictional force will cancel any applied force that's parallel to the surface up to a certain limit. Okay, so just like the normal force cancels any force that's perpendicular to the surface, the static frictional force will cancel any applied force that's parallel to the surface up to a certain limit. Okay, the limit of the static frictional force is given by this formula right here. The maximum static frictional force is equal to a constant times the normal force. Okay, so the larger the normal force, right, the more force that's pushing against that surface, then the larger the frictional force that resists sliding the object against the surface. Okay, so if, for example, we're looking at a flat surface, then the heavier the object is, the larger the gravitational force that's pushing down against that surface, the larger the frictional force. So hopefully that just makes sense. This constant that appears in the equation is called the coefficient of static friction. And this kind of looks like a U. This is actually a Greek letter, mu, and you denote it with a U, and it's kind of got this long tail in front. And then we use a subscript S to denote that this is the static frictional force. Okay? So we've talked about some Greek letters before. There was theta and delta. This is just another one. So the static frictional force perfectly cancels forces that are parallel to the surface up to a certain point. So let me kind of draw like a little picture here. So if I have, say, some object, and I apply a force to this object, the static frictional force will be equal and opposite to that applied force. Okay? Now if I increase the applied force, so say for example, I now apply a really, really large force, as the applied force gets larger, so as this force gets longer and longer and longer, eventually the applied force will exceed the maximum static frictional force. And when this happens, we get a new type of frictional force that arises, which is called the kinetic frictional force. So when the static frictional force is exceeded, the object will begin to slide and a new frictional force will appear. So this frictional force is called the kinetic frictional force. This is the frictional force that is exerted on a moving object. Now, there's two things to understand about the kinetic frictional force. The first is that the kinetic frictional force is constant whenever the object is in motion. The other thing I don't have on this slide, but it's a very important thing to understand about the kinetic frictional force, is that the kinetic frictional force always opposes the motion. Okay? So this means that the direction of the kinetic frictional force is always opposite the direction of your velocity. Now the frictional force is given by this formula right here. Notice it's almost identical to the maximum static frictional force formula. Okay, so the kinetic frictional force formula is proportional to the normal force, and the constant of proportionality, that's this mu here, this is called the coefficient of kinetic friction. Okay, so it's the same thing. We use a mu, and now we use a subscript k to denote that we're talking about kinetic friction. So let's work through a couple of simple examples. The first example says, a skater has an initial velocity of 7.6 meters per second and is sliding across the ice. The coefficient of friction between her skates and the ice is 0.1. how far will she move before coming to rest? Actually, before I even solve this problem, I forgot I wanted to do something. Let's look at this formula right here. So on the left side, we have a force. This is the kinetic frictional force. And on the right side, we have mu times the normal force. So if we apply dimensional analysis to this, we have the units of my frictional force are equal to the units of mu times the units of the normal force. So this is newtons are equal to the units of mu times newtons. So looking at this, we can see that mu, the coefficient of static friction or the coefficient of kinetic friction, whichever one we're looking at, has to be unitless. Okay? This means you have to be very careful when we're dealing with friction, because if you drop a factor, if you forget the coefficient of kinetic friction or static friction, your units will still work out, okay? But you'll get the wrong answer. So it's very important that you remember to keep this mu whenever you're doing a calculation. You don't accidentally drop it somewhere. So I wanted to go over that because here I say mu is 0.1, and I don't provide any units. I don't provide any units because this is a constant. It's unitless. Okay? Now, anytime we have a problem like this, remember the first thing that you want to do is you want to look at the problem and you want to say, well, what is this telling me and what am I asked to solve for? So here I pretty explicitly say V naught is 7.6 meters per second, and I tell you the coefficient of friction is 0.1. There's a little bit more information here. I tell you, I ask how far does she move before coming to rest? Okay, remember, this is like one of those key words when I say the object comes to rest or it starts at rest. So here we see that V final is equal to 0 meters per second. Finally, we can see what I'm looking for, how far she moves. So delta x is what I'm asked to solve for. So let me open up a blank screen here. So let me write this down. My V initial, that was equal to 7.6 meters per second. Mu is 0.1. V final is equal to 0 meters per second. And delta x is what I'm looking for. Okay. Now the next thing it's always a good idea to do is draw a free body diagram. So here we have this beautiful stick figure here. And there are three forces acting on this person. Okay, there is the force due to gravity that points down. There is a normal force that points up. And then there's this frictional force that opposes her motion across the ice. So this is if she was moving to the right. Okay? Now, let's take a step back and think about how can we use this information that was given to us to solve for delta x. So, what Newton's laws allow us to do is it allows us to relate this frictional force to the acceleration of the skater, or maybe I should say the deceleration of the skater since she's slowing down. And here I've been given the initial velocity, the final velocity, and I'm asked to solve for delta x. So if I use Newton's laws and I solve for my acceleration, or I find a formula for my acceleration, I can use the kinetics formula, V final squared equals V initial squared plus 2a delta x, to solve for delta x. But before I do this, I need to figure out what my acceleration is. Okay? So looking at this, Newton's second law, it tells me the sum of my forces is equal to mass times acceleration. Okay, well, again, looking at this, my normal force is perfectly canceling my gravitational force. So my net force is just equal to my frictional force. It's the only force that's not canceled out by anything else. So we have my frictional force, actually I should say this is a kinetic frictional force, is equal to my mass times my acceleration. The kinetic frictional force, remember, is equal to the coefficient of kinetic friction. Actually, I should put a K there. This is kinetic friction. Times the normal force. Now, looking at this picture up here, I'm not even going to write any of this down. This is really easy. The force due to gravity is mg, and my normal force cancels any force that's perpendicular to the surface. So my normal force cancels the gravitational force, so my normal force has to have a magnitude of mg. So plugging that into here, this is mg, we get that this is mu k mg is equal to mass times acceleration. Now some of you may have been worried at the start of this problem that I didn't tell you the mass of this skater. And you may think we're not going to be able to solve the problem. You can see now that the masses cancel out. So the frictional force increased with the mass of the skater, and the inertia also increased with the mass, so it canceled out. So now we see that the acceleration is just mu sub k times g. So plugging this into this kinetics formula up here, so let's rearrange this to solve for delta x. So we see we have v final squared equals v initial squared plus 2a delta x. Let me subtract the v naught over to the other side. So this is 2a delta x is equal to v final squared minus v initial squared. So delta x is v final squared minus v initial squared divided by 2a, or v final squared minus v initial squared divided by 2 mu sub k g. And actually, I should be a little bit careful about this. If delta x is a positive number, if I say that to the right is a positive x direction, okay, then my frictional force points in the negative x direction. So my acceleration is technically, it would be a negative mu times g. So I have a negative mu times g here. My final velocity is 0. My initial velocity is 7.6 meters per second. So if I plug this into a calculator, let me see, I've got a cheat sheet here. I see that this is going to be equal to 2,940 meters. So if we just plug these numbers in, because I know my initial velocity, I know mu, and I know g is equal to 9.8. So let's go back and look at another example. This example says it takes 4 seconds for a block starting at rest to slide down a 10-meter ramp that's at an angle of 30 degrees. What is the coefficient of kinetic friction between the block and the ramp? So again, the first thing we want to do is we want to look at this and figure out what our known values are and what our unknown value is. So it takes 4 seconds, so this was delta t. Starting at rest, v naught is equal to 0 meters per second. Okay. Delta x is 10 meters, and the angle of the ramp is 30 degrees. Okay. And so basically, again, taking a step back and looking at this, what we're going to do is, here I've been given a whole bunch of kinematics. I've been given delta t, v naught, the delta x. So using all this information, I can figure out the acceleration of the block down the ramp. Once I know the acceleration of the block down the ramp, I can relate this to the forces, and I can figure out what my coefficient of kinetic friction is. That's what I'm solving for, so I'm looking for mu sub k. So that's the idea. So the first step here is figuring out what my acceleration is. So let me open up a white screen and let me write down these knowns. So this was delta t, this was equal to 4 seconds. Let's see, I've got this written down on a piece of paper here. What were my other knowns? V naught, I started from rest, was equal to 0 meters per second. I have that delta x is equal to 10 meters. Theta was 30 degrees. And what I'm looking for is mu sub k. Okay. So I'm going to try to find my acceleration. So looking at what I know, I've been given delta t, so that's usually a pretty good hint. The formula we want to use is delta x is equal to 1/2, not g, acceleration times delta t squared plus v naught delta t. And in this case, this v naught is 0. So now if I solve for acceleration, so if I multiply by 2 and divide both sides by delta t squared, I see my acceleration is 2 delta x divided by delta t squared. So if I plug my known and unknown values into this, I see that this is equal to 1.25 meters per second squared. So this is my acceleration. So actually, let me just go ahead and open up a new screen, because I'm probably going to need some more room. So let me write this down. We had that delta t was equal to 4 seconds, v naught was equal to 0 meters per second, delta x was 10 meters, theta was 30 degrees, and now I have my acceleration is 1.25 meters per second squared, and I'm looking for mu sub k. Okay, so let's go ahead now and consider a free body diagram. So we have a box, it's sitting on a ramp. It's at 30 degrees. So remember, when I have a box and it's on a ramp like this, right? Say, let me just go through this again. Here's my force due to gravity. Here I get a right triangle from the ramp and the force due to gravity. So this thing right here, if this is theta, this is 90 minus theta. This angle up here is 90 minus theta. If I'm decomposing this force, I'm trying to figure out what this component is. It's perpendicular to the surface. I can see that this angle right here then is 30 degrees. Okay, this angle in this triangle here. So let me go ahead and draw this again a little bit bigger. Draw this up here. Here's my force due to gravity. Here is my y component. Here's my x component. And this angle at the top is 30 degrees. Okay, so the forces that are acting on the block as it slides down the ramp. Okay, if I draw a free body diagram of this, okay, so I'm going to have to erase something. Let me erase this to give myself some room. The block, if I draw a free body diagram of this block, here's what we have. We've got, here's my ramp, here's my block. So I've got a force due to gravity that points down. I've got this normal force that points up, perpendicular to the ramp. And then we've got a frictional force which is trying to slow the block down as it slides down the ramp. And of course I can decompose this frictional force, the gravitational force, into a component that's pushing the block down the ramp, and then this component of the force that's pointing perpendicular to the ramp. And I need to know both of these components because the frictional force depends on the normal force, which depends on the y component of my gravity. Again, treating this coordinate, so y is up and away from the ramp, x is sliding down the ramp, okay? So my normal force is equal to the y component of my gravitational force, and I need that to calculate the frictional force. And then the other force that's causing the object to slide down the ramp is this one right here, okay? So just applying Newton's second law, the sum of my forces is equal to mass times acceleration. And in this case, the forces in the y direction are canceled, so let me just say my forces in the x direction are equal to mass times acceleration, because I know the y forces are going to cancel out. So the forces in the x direction, if I call down the ramp the positive direction, well, I've got the x component of my gravitational force going down the ramp, and then I've got this frictional force, this kinetic frictional force that's pointing up the ramp. So that's got to equal mass times acceleration. The force going down the ramp, the gravitational force, notice this is opposite the angle 30 degrees, okay? So this is going to be mg sine of 30 degrees. The kinetic frictional force that's opposing the block as it slides down the ramp, okay, this is going to be equal to mu sub k times the normal force. And I can solve for the normal force, right? The normal force is equal to the magnitude of the y component of my gravitational force. So this is going to be, right, this is adjacent to the angle 30 degrees, so we have that's equal to mg cosine of theta. So here we've got mg sine theta is the force due to gravity down the ramp. And then the frictional force is minus mu sub k mg sine of 30 degrees. And that's equal to my acceleration. So So we can see here the masses, so that's equal to mass times acceleration. The masses cancel. I know what my acceleration is. I know what g is. I can calculate sine and cosine of 30. I'm sorry, this should be cosine. This is, right, the normal force was adjacent. So this is cosine here. I can calculate sine and cosine with a calculator. So at this point, the only thing I don't know is mu sub k, and that's what I was asked to solve for. So, I hope I don't run out of room. If I move this to the other side and I subtract off the a, I get that mu sub k g cosine of theta is equal to g sine of theta, I say theta 30 degrees, minus a. And then finally I see that mu sub k is going to be equal to g sine of 30 degrees minus my acceleration divided by g cosine of theta. My computer really doesn't like it when I write near the bottom of the screen. So if I plug all these numbers into a calculator, right, g is 9.8, I can calculate sine and cosine of 30 degrees. My acceleration, remember that was 1.25 meters per second squared. I see that this is equal to 0.43. So that was my coefficient of kinetic friction. So that was a pretty long, somewhat challenging example, and I think I'd like to end the video there. And in the next video, I'm going to talk about Newton's third law. And this is the law that says that for every action there is an opposite but equal reaction. So explain what that means specifically, and then we'll work through a few examples.